Can we get started? Okay, this tutorial 4. Any questions on number 1? Anyone has questions how to get started? You all hear me in the internet? Okay, thank you, Sun Yi Kwan. Any questions on how to get started on this number 1? Anyone? Yes, sir. How to get started? Yeah. What do you all think? How do you get started? Yes, that's right. We draw. Let's start drawing first. What do you draw? What do you draw? XYZ, right? Okay, so make sure you know how to draw XYZ correctly. Yeah? It may sound obvious, but you need to get the direction of your Z correctly after you've defined your X and Y, right? So I presume no question on that. In this case, I am lazy to draw Z. So I draw 2D only, in this case, X and Y. And then I decide to visualize the magnetic field in the YZ plane. All agree the magnetic field will be in the YZ plane? Yes, right? So I just draw 2 lah. How you want to draw it, up to you. Huh? Yeah. Okay, so what's next after we have drawn? Yes, we need to find a source point. We need to find a source point, locate the first source point, right? So to locate the source point, there are 3 wires. Which wire are you going to use? Yeah, exactly, right? All want to choose the one part of the X because it's the easier one to use, right? So we're concentrating on this wire on the bottom here, this X wire. So it's parallel to the X-axis. Its length is W. Hence, it varies in X value from minus W/2 to plus W/2. So we're going to choose a source point. So always choose positive. Whenever there's a variable, you choose positive. So in this case, the variable is X, right? So we choose positive X somewhere here. What's the Y value of this source point? Yeah, so you have to label, okay? Because along this line, the Y value is a constant, right? Agreed? It's a constant. So you just have to label whatever that value is now. Let's say that value from that line to the center is H. Then that means the Y coordinate of that source will be yes, plus H or minus H? minus h, right? And then the z value will be 0, right? So now you got your source point, right? The source point location is x equal to x, y equal to minus h, z equal to 0. What's next? Yes, so we are going to use Biot-Savart's law, right? Up to this point, we need to use Biot-Savart's law. Do you need to memorize Biot-Savart's law? Yeah, so make sure you know how to use the formula sheet from your exam appendix. I'm going to open it and make sure you know how to use it. Huh? Okay, so here's our electric and magnetic field. Tell me which one is Biot-Savart's law. All agrees the third one, right? This one, right? So what does this say? Can you tell me what is on the left-hand side? Okay, thank you. So read it like this, okay? Read it like this. The magnetic field vector generated by a small length of wire dl vector with a current I passing through it will be given by this formula, 1/4 pi integrate closed circuit I dl, that vector as we say just now, cross with the r vector divided by r cube, right? I'm going to use this one, the rightmost one. Huh? Okay, so where is that dl vector in our figure? Yeah, it's this source point here, right? This source point, but you must have found finite length, right? What's the length of that source point? It's your dx, right? And that dl vector is basically that dx magnitude times direction is, yes, ax positive, right? Okay, so that's what we have for our dl vector in our Biot-Savart's law. Huh? This is our dl vector, right? Just now we saw Biot-Savart's law. It's our dx vector. So our dx vector is given by dx ax. Dx ax positive. Huh? Okay, and then what is this r vector? The r vector is from the source point to the field point, right? Field point is we want it at the origin. So what's the answer for r vector? You can use field point minus source point, or you can see it from the figure, right? Okay, he has already found what is h in terms of w. Okay, and never mind, we just put it as h first. Later on, you can find h as a function of w, right? Yeah, from the equilateral triangle here. Okay, so for the time being, I just leave it as h first. It's a constant that we can find as a function of w. Okay, all agree with that r vector, which is pointing from the source point to the field point. Huh? The field point is at the origin here. Okay, so therefore we plug everything in. I mean, this denominator r is just the magnitude of that. So you have x squared plus h squared square root. Plug everything in, we have r. Okay, so when we plug in, we need to do this cross product, right? So how do you do this cross product, which is this cross this? How do you do this cross product? Everyone know how to do a cross product of do these two vectors that only has two unit vectors? Early on, we did this cross vector of 3 unit vectors, right? So we need to use this determinant to find, right? Now it's only 2 unit vectors. So what do you do? Yeah, just expand it, just multiply one term by term, right? So we take this term of dx, cross with this term of r first, right? What's the answer? this one first, huh? This cross with this, huh? That means AX cross with AX. 0, right? AX cross with AX is 0. Then next is this cross with this, right? Okay, so AX cross with AY is AZ, right? So therefore we have the AZ direction, and the scalar part is this dx times the h, right? Okay, so h dx or dx times h, up to you which order you want to put it. Okay, denominator is everything scalar, right? So we leave it there. And then 1/4 pi also. So that is only the h produced at this point, the field point, due to this small section of the wire. So you have to, sum them up from the section, small section starting from this leftmost all the way to the rightmost. So that so-called summing in maths is integration, right? So we integrate from x equal to minus W/2 to plus W/2. Then we'll get the total magnetic field vector due to the entire wire, that wire number 1 that we talk about. Okay with that formulation? Okay, so once you formulate up to here, is actually the rest is just algebra already, right? You look at the things that are constant with respect to x. So h is constant, so hi divided by 4 pi are all constant. So now I'm left with integrating. Actually, AZ is also constant, right? So AZ can also come out, or you put it the other side, up to you, huh? AZ is a unit vector. So when we integrate dx divided by x squared plus h squared to the power 3/2, you're given that the solution of that integration is this, right? So in place of a squared is h squared, right? So that's how we get this answer here. X divided by h squared into x squared plus h squared to the power of half. So I need to put x value varying from minus x/2, minus W/2 to W/2. So if the rest is all algebra already, okay? So you should find that the coefficient, the scalar part is 3i/2 pi w. After you substitute what is h in terms of w now. So what's h in terms of w can be obtained from this triangle here, right? This is 30 degree because equilateral triangle is 60 degree. So halfway is 30 degree. And this is our h that we try to find. This is our W/2. So tangent 30 degree is h divided by W/2, right? So from there you get h is W/2 square root 3. Yeah. Okay with that? Okay. Are you okay now? Follow. Okay. So we are now done with this magnetic field due to this wire, right? Okay, so you may want to visualize it and see whether it's correct or not. So that's what I'm doing on the right-hand side. So all agree, if this is our x-axis, this is our x-axis, this is our y-axis, our z-axis is coming up like that, right? So the wire is here, right? At the y value of minus h, the wire is here. So magnetic field, if the current is flowing this way, will be like that, right? So therefore, it's in the YZ plane, right? That's why I sketched the YZ plane. So the wire itself is here, right? Center, here, right? And it's coming, which direction? Going into the board or coming out of the board? Out of the board, right? You look at because my Z is labeled up. So Y cross Z will be X, right? Y cross Z will be X, so X is coming out. So our current is in the positive X direction. So therefore it's coming out. So the magnetic field is concentric circles around that wire center, right? Like that, in the anti-clockwise direction, right? Which one are you interested to draw? So I draw this circle, so I draw this circle, so I draw this circle, so I draw this circle. Which one are you interested to draw? Exactly, the one that crosses the field point that you're interested. So in this case, your field point is at the origin. So draw the one that crosses the origin, right? So remember, basically this circle means constant scalar part of the h, right? That's what we are visualizing actually. Okay. So therefore, at you are looking at it at the center, at the origin here, right? So where's the direction of the magnetic field? So at any point you're interested, you should draw a tangent to this circle, right? So the tangent to this circle is pointing that way, right? So therefore it's positive AZ direction, which indeed Biot-Savart's law, when we solved it, we got positive AZ direction, right? So now you're convinced that, visually you can see it's correct. Always do that check, because sometimes if you make a mistake in a cross product, you get the wrong answer. So this is a visual way to check. Okay, so we're done with the magnetic field due to this wire. How about this wire, the second wire here? What do we do? Yeah, just rotate it, rotate it until it's parallel to the x-axis. So it'll be the same, right? Same thing for the third wire, right? So therefore, by symmetry, we can say that it's 3 times. So that's how we get the final answer. What's the units for magnetic field? Yeah, for us, we like to use ampere per meter because in real life, normally we inject current to generate the magnetic field. Yeah, inject current, so that's why the ampere comes in. Those of you from physics background, you'll say Tesla, right? Yeah. Okay. Can we move on? Any other questions on it? If not, let's move to question 2. So same thing again. How do we get started for question 2, part 1? Question 2, part 1. Yes, thank you. Draw a figure and identify the source point. Again, it's the same thing, okay? Always start from there. Why is there a need to identify the source point? Why can't I just use the formula that, hey, this current density given to me. Current density times area will give me current, right? So can I just take this current density and multiply by the area, which is pi a squared? Why cannot? Why cannot? Yes, because the current density is non-uniform. Non-uniform. So you have to make sure your area is small enough that it's uniform. That's your first step. That's why he says source point, because you have to make that area small enough until it looks like a point, It looks like a point. At the point, the current density is constant, right? Yeah. If the area is small enough, the current density over that point, that small area is constant. Yeah. So that's what we have to start from. Okay, so let's try and draw something like that. Let's draw something like that. Okay, so I'm going to draw X coming towards me, Y in the right, horizontal right, and then Z will be going up. Right? Okay, and then I draw the circle with the radius A. I draw a circle with the radius A in the XY plane. Current density is given by this equation. So if you look at this equation, where is the highest current density? If you substitute R equal to 0, you get 1 here, right? If you substitute R equal to A, you get 0 here, right? Yeah, so R equal to 0 will have the highest current density. And then it becomes weaker and weaker, weaker and weaker as you go out, right? Is the current density uniform in phi? Going round it, is it the same? Yes, right? You can notice it's the same, uniform in phi, but varying with R. Varying with R. Okay, so that gives you a hint of how you want to make that source, right? Small source, right? That small area. You have to start with a small area. So you need to choose appropriate coordinate system. You're going to use Cartesian or you're going to use cylindrical? Yeah, exactly. Use cylindrical will simplify your calculation, Doesn't mean that you can't solve it using Cartesian. It's just a bit longer steps. Yeah. So we're going to use cylindrical. So how to make a small area? We're going to choose a small ds, which is located at some r from the center, right? Which is a variable that we're going to eventually vary from 0 to a. And then we need to increment the angle a little bit, right? Which we'll call it d phi, right? Because the angle in cylindrical coordinates is measured as phi from the x-axis. So it's that way, right? So we increment it a little bit by d phi at some phi value. Okay, so what is that small area? What's the value of the area? Yeah, r d phi dr, right? R d phi dr. Where's the direction of that area? Where's the direction of the area? All agree is AZ, right? Positive AZ or negative AZ? How do you say? How do you determine whether the area you want it up or you want it down? Okay, your current is given by J dot ds, right? Your current is J dot ds. So if your ds direction is same as your J, then the current direction will be positive in the same direction as J. If you choose it the other way around, then your current become a negative of where your J is. So obviously you want it to follow J, right? So therefore you use the same direction for your ds as your J. Yeah, just use it like that. Your ds direction will be same direction as your J. Okay, so hence that's why we have ds as a vector is r d phi dr az. Can I swap this order? dr and then d phi? Yes, I can do that if I want to. But if I do that later on, I'm going to integrate with respect to dr first, then do a d phi, right? Whereas if I'm going to do a d phi first, then dr, the difference is if I do a d phi first, I'm going round first, right? So I form what we call a ring area of width dr. Yeah, a ring with a width dr. Then we're summing all those rings, right, from the innermost to the outermost. This is more natural actually because it's independent of phi, right? We say, right, the current density is independent of phi. If you do it the other way, you do a dr first, you're actually forming this arc area first, right? This arc area, and then you're going to sweep this arc area around. Anyway, up to you which way you want it. I think it's easier if you do a ring first. So that's why I do a d phi first, then followed by dr. So the first integration is very simple, right? Just multiply by phi, right? So multiply by 2 pi. Next, integrate with dr, right? This is also very simple integration. Just expand out, right? So expand out, you have r times 1 is r. Integrate with r is r squared over 2, right? And then expand out this one, you have r cubed over a squared. So integrate r cubed, you have r to the power 4 divided by 4, right? In the a squared there. Okay, so then we put r from 0 to a, do some algebra, you find that it's I naught. Is everyone okay with that? Okay, next part is use Ampere's law to find the magnetic field intensity at this point and this point. Okay, this one is important. I want you to discuss group by group how you want to solve this. Each group, please discuss how you're going to solve this. This one is very important. Those on the internet also, please participate. I want you to tell me how you solve the second part of question 2. Where do you start? Draw what? Yeah. draw something that you're going to reflect what you're going to use for Ampere's law. So you have to know how to interpret Ampere's law first. Then you can draw what you want to solve Ampere's law. That's what my recommendation is. Okay, so let's first understand Ampere's law. What is Ampere's law? Let's bring out exam mathematics again, right? You don't have to memorize it. Which one of these is Ampere's law? Which one is Ampere's law? Yeah, fourth one. This one here is Ampere's law. Okay, now next very big challenge. Read it out in your own words, what it says. That means read it out in a way that you know how to use it. What does it say? This is very important, okay? If you know how to read the symbols out in words, it shows a big step already. Are you going to read it out starting from the left or starting from the right? Start from the middle. Oh, very easy. Current. Okay. Nothing else you can say, right? It's the current flowing. Okay. So all agree right hand side we already covered in first part, right? So no point talking about that either, right? I'll be repeating myself. So now tell me how we read this in words. Integration of the magnetic field. That is too short. More precise, more precise. Closed field magnetic. Closed loop magnetic. Closed loop. Closed loop. Okay, I'm looking for the keyword. The keyword is closed loop. This integral sign with a circle around it is closed loop. So what creates the loop? Which create the loop? I mean, there are two terms there, right? There's the H and there's the DL, right? Is the DL that create the loop or the H that create the loop? DL is the one that create the loop. You choose a path that you want to go and come back. Okay, that's your DL path, okay? You're going to go around and come back. Do you want to go around in a circle and come back? Or you want to go like a triangle and come back? You want to go like a square and come back? You want to go like an oval and come back? Arbitrary shape and come back? Which one? Any of this is fine, you know? Any of this is fine. Any of this is fine. Arbitrary shape, good luck to you. How are you going to put that in an equation, you know? So you can only do arbitrary shape if you're using numerical integration, cross loop. You cannot if it's you're going to use your hand to do it. So it got to be expressible in analytical form. So triangle, fine, right? Divide into 3 segments, you can solve, right? Rectangle, divide in 4 segments, you can solve, right? Circle, even easier, right? So which one? Circle. Why circle? Why circle? Why not a triangle? Louder, louder. I'm hearing a very keyword. Because the magnetic field around this circle is the same. Excellent. That's how you choose the path. Choose the path such that you can easily evaluate this H dot DL in the scalar path. Yeah, because if you choose a path that the H is a constant, that's so easy to solve, right? That's exactly her point. Choose your path where the magnetic field is constant. So we all know the magnetic field is a constant in a circle, right? So your path should be a circle. Yeah. Okay, so now we visualize. Now we start to visualize. So what do you visualize? Is it very clear to you? What do you visualize now? What do you draw? You have to draw your path, right? You got to draw your path, right? So where is the path you're interested? To be circle around the wire, right? So in this case, it's not it's a cylinder, right? Not a very small wire diameter, right? It's a cylinder. So you used to be drawing around the center of that cylinder, right? At what kind of circle size? What circle size will you be drawing? Well, you got to ask yourself, where do you want your field point, right? Yes. Where do you want to evaluate your field point? This. What is this? A over 2? Is it X value? Is it R value? R value. Okay, it's given as cylindrical coordinates. This is R value. This is phi value. This is Z value. Okay, so hands up those of you who don't know how to locate the position of this. Okay, start from, I give you Cartesian. X equal to 2, Y equal to 3, Z equal to 5. How do you locate that point? You go X equal to 2, Y equal to 5. Okay, so you go along the axis, each of the axis, and then you pinpoint, right? Okay, where is the field vector? It's basically from the origin pointing to that point, right? That's your field vector, right? Okay, cylindrical, how do you do that? Yes, you start with a circle. So that, yes, so you basically draw a circle of AO2 in this case, right? Because the R is AO2. So your first thing you do is from the XY plane center, you draw a circle of AO2. Next, your phi is 0. What do? You draw a straight line from the center, the XY center, at the angle of whatever that is now. If let's say we go on to the second one, let's say second coordinate here is 45 degrees, pi by 4. What do? You draw an angle of 45 degrees from your x-axis, because that's how phi is measured. So you draw a line. The intersection of that line with the circle is your point in the XY plane. Then finally, given by that Z value, you go up vertically. That's your point. Okay, so that's how you visualize cylindrical coordinates. The degree is 0, then the point in the Y. X. Yes, x-axis. Yes, that's how it's defined. The angle phi starts from x. Okay, so this is my positive x. Start from x, 10 degree, 20 degree, 45 degree, 90 degree, 135 degree, 180 degree. After that, do we say 200 degree? No, never say 200 degree. It will be minus. You have to go by this way. You go by this way. Minus 45, minus 90, minus 135, minus 180. Yeah, so polar coordinates always default maximum angle is within plus or minus 180 degree. Sure, I mean, yeah, it's in that axis. Yeah. Okay, so those are the basics of cylindrical coordinates. Okay, so now that's important because you need to know how to visualize. If you cannot visualize, you can't find the direction in Cartesian correctly. Okay, so all agree that we're going to draw a circle at the radius of AO2 because we need to pass through this field point. This is basically our loop that we're going to go around in our Ampere's law, right? And on and behold, you know that the magnetic field around here is also constant. Agreed? So what's the general expression for your magnetic field? Give me a general expression for the magnetic field. Give me a general equation for magnetic field that will fit any magnetic field in cylindrical coordinates. H as a vector is equal to, we don't know yet, some coefficient, which is H in the radial direction with a unit vector AR plus H with a suffix phi, that means the H in the phi direction coefficient times A phi, that unit vector, plus H in the Z direction, yeah, that coefficient HZ times AZ unit vector. Okay, so that will be a general expression that will work for all, So there's three terms basically, right, in cylindrical, because in general, you could have AR unit vector, some finite AR unit vector. You could have some finite AZ unit vector. Just like if you want a general expression for Cartesian, you will have HXAX unit vector plus HYAY unit vector plus HZAZ unit vector. Agree? Now, in this case, do you have AR unit vector? For this problem, do you have AR? What would the magnetic field look like if you have AR component? You have AR component. Let's say magnetic field is AR component. What would it look like? Think of your E field. Your E field is radial, right? I mean, this figure, we are visualizing the magnetic field, right? We are visualizing the magnetic field. So if you have AR component, what would it look like? Is it still circle? Or is it going to be like arrow pointing out from the wherever the source point is, which is the center of this figure? Radial, yeah. It'll be pointing out. It'll be radial. It'll be like the E field, going out. So obviously no, right? You don't see magnetic field going that way, right? It's all like that, right? So that implies AR is 0. A phi is finite because it goes round, right? How about AZ? Is AZ finite or AZ is 0? Is it 0? Why? That doesn't answer why. Why is AZ component 0? Go and visualize. Okay, this is x-axis, this is y-axis, this is z-axis. Why this component? Cylinder is here, right?
Yes, it goes on the xy plane.
Why can't you have some component like that? Why can't you have some component like that? Which cancel each other?
The y of z.
Yes, because top and bottom cancel each other. This cylinder is infinitely long along Z. If it's only finite length and lie on the top, then no, you can't say that AZ component is 0. Okay, so those are the reasoning why we now say that the H field is just some H phi coefficient times A phi unit vector. Okay, the other two term is 0. I just explained to you why they are 0. Okay, so this is our expression. We're going to put it into Ampere's law. So this is our Ampere's law. Okay. Okay, so this is our Ampere's law. So we need to solve for H is this, right? We already said, right? Okay, so H phi, we need to find what it is. This, our target is to find H phi. A phi is the direction of the H vector. This DL is the loop that we're going to go around, right? And we already said we're going to choose a circle at the same radius as our field point, right? Yeah, where the h remain constant around it. So this is our DL path. Right? So DL is just a small line segment in that circle, okay? Small line segment. So in cylindrical coordinates, what that is going to be at some radius, which is constant at a over 2, right? We need to pass through a over 2. So we have a radius is a over 2. The length, arc length is basically that a over 2 times d phi, right? Located at some angle phi, right? That's our DL. Huh? So our DL vector is given by this equation here, right? So it's in this direction, right? A phi, right? All agree with that? Okay with that? Okay, so now the next thing is just do this dot product, this vector dot with this vector. So I have a phi dot with a phi is 1, right? A phi dot with a phi is 1. So therefore I have h phi times a over 2 d phi, right? So h phi a over 2 d phi. And I need to then next sum up until it goes the whole loop, right? So that is the integration from phi from 0 to 2 pi. So of course, the answer of this is very straightforward, right? It's a over 2 times 2 pi, right? A over 2 times 2 pi times h phi, right? And then on the right-hand side here is the total current I, right? The total current I is your part 1, right? All you have to do is just use this equation again. But this time, your current only flows up to a radius of a over 2. So from 0 to a over 2. And then you put that in and then solve, you can get your h phi value, right? Which is this value. Okay with that? Is there a need to do integration in this case? Actually, no need now because the h is constant. Your everything is constant, right? You know, so actually it's just the loop length. Yeah, this thing is just a loop length. So 2 pi times the radius, right? Yeah. So of course, you will see the answer is the same now. 2 pi times the radius. Okay, so that means our answer to this H field that we're trying to find is this coefficient, which is this value, times a phi, right? Direction is a phi. But we are interested in it to be evaluated particularly at this point. So we need to evaluate a phi at that point. So what is a phi at that point? That point is here, agree? This is the point a over 2. So I draw a circle a over 2. Phi angle is 0. It means it's along the x-axis. So intercept is this point, right? This is the point I'm interested in. Where is the direction of the magnetic field? Magnetic field is going around like that in anti-clockwise, right? So therefore, direction is this, right? Which is AY. Yeah. So that's how we, yeah, change that A phi into AY now. This one, yeah. Okay with that? Okay, now we go and work out the second point. Second point is that we want it at this. So radial direction is 2a. Angle phi is pi by 2. Z is 0. Okay, so same again, we're going to use Ampere law, which means that we need to draw a path that passes through that point. Where is that point we're interested? We draw a circle of radius 2a. So this blue circle is 2a radius. Phi equal to pi by 2. So you go from x-axis towards the y direction by 90 degrees, right? So you end up here, right? That's the point. So straight away, you can tell what's the answer for the direction of that vector already, right? Yeah, negative ax, right? You can see the label there, right? It's going that way, yeah? Yeah. So this negative ax. My drawing should skew a bit more, huh? That is lying in the xy plane. Yeah. Okay, so we already got the direction of this sphere. We need to h phi, find the coefficient of it. The coefficient of it, we are going to use Ampere's law, right? So we say that, hey, this integral is straightforward because it's just going around the path with a constant h, right? That h phi, right? So it just multiply by the integral will give you the total length of that path. So what's the total length of that path? 2 pi times 2a, right? So 2 pi times 2a will give me 4 pi a, right? Times the magnetic field that we're trying to find, right? Yeah, is equal to the total current enclosed. What is the total current enclosed? With a radius 2a. We have found in the first part up to a radius of a, the total current is I, right? Is there any current flowing from A to 2A? No, right? Yeah, because it's given the current density is 0 beyond the radius of A, right? So therefore, the total current is just I naught, right? So that's how we get this coefficient part, I naught divided by 4 pi A in the direction of minus AX. Okay with that? Any questions, anyone on this? I suppose I'm a little bit fast. Yeah, just about finished within 1 hour. Okay. Any questions, anyone? If you have some fundamental question, please ask. How about last week lectures? Any questions on last week lectures? Okay, if not, we move on to the next part, which is asking ourselves, what do you need to solve next week tutorial, right? Okay, what do you need to solve next week tutorial? Here's next week tutorial. Can you tell me what do you need? Flux density. You need to understand flux density given by the symbol B. Analogy with electric field is D, right? D is the flux density in electric field, right? So if you go analogy with your D, remember D is equal to epsilon E, right? So what is your guess of B is equal to? Mu times H, basically. Yeah. B is equal to mu times H. Okay, that's your lecture notes from last week. I think the remaining sections are remaining more parts of it. I think last week we did say that you only need the first two, is it? So 10-3 from last week lecture notes is actually magnetic flux density, you can see. So it's given by this equation. Yeah. B is equal to mu H. So mu is permeability of the medium, right? Which is given by mu R times mu naught. Mu naught is a constant for free space. It's a constant. Mu R is the one that changes depending on the material. And even with the same material, it may change in X, Y, Z coordinates if it's non-homogeneous. Any questions on this? Okay, of course, next part is talk about flux, right? Just like electric field part also, right? After you got flux density, it's only natural to talk about flux, right? So flux is flux density times area. So same thing again here. Flux is flux density times area, but this case magnetic flux density. So you start with an area that's small enough that is magnetic flux is constant, yeah, and then double integral to get the total flux. Okay. So this may then rings a bell for Gauss law, right? Gauss law say, hey, if you calculate the total flux enclosing a volume, So if you have cube, you have 6 surfaces that enclose a volume. If you have a sphere, it's only 1 surface, right? That enclose the volume. So here also the same thing, you will talk about that also. But in this case, it says that the total flux enclosed is always 0. Total flux enclosed is always 0. So for static magnetic field, since there are no isolated magnetic charge. So if you apply divergence theorem, it says divergence of B is 0. It's a nice summary of electric field, magnetic field. So one note here is that, you can see curl E is 0 for static electric field. Curl H is current density. So in other words, this tells you that, hey, electric field never curl around, okay? Never curl around, don't go round and round. Magnetic field will curl as long as you have some current density. Yeah, that's what it's saying. Whereas divergence of flux, right? So that means because flux, this flux density is related to magnetic electric field, right? This electric flux density D is electric field related to electric field. So this divergence of D is equal to rho V, means if you have some volume charge, then you have some electric field that's radiating, yeah, in the radial direction. Whereas there's no radiation of magnetic field, right? It's always 0. Force is another interesting thing, right? So if you want to calculate force in the presence of an electric field, it's just the charge Q times it for electric. And then for magnetic is a charge times the cross product of the moving charge, right? That U, the moving charge velocity, I think the U vector cross B. Okay, so that's one set. You have to go through all this remaining. So 11-1, I think we'll talk about flux, Faraday's law, which you need to solve your first question. Okay. This is a very important summary. If you have electric charge, it creates electric field, right? It creates the electric field. If your charge is moving, you have current, right? And if you have current, you will generate a magnetic field. Now the question is, can you generate a magnetic field, electric field with a given magnetic field? Can you generate an electric field with a magnetic field? Yes, right? That's how we generate electricity, right? All electric generators use that principle. So that means we may have like a magnet that create a static magnetic field. They move a coil around it, right? So that movement is kinetic energy, which can come from, like, for example, hydroelectric power, the water movement, or it can be steam that makes the turbine spin. So all of them work on the basis that you have to spin something, you have to move a coil to generate that electric current, right? The electric current. Okay, so that's basically your question one, you know, your EMF generated, right? Here's your question one, right? So your question one says that, hey, I have this electrical circuit, right? So is there a voltage across this resistor and this resistor? There is if there's a current circulating, right? Okay, there is if there's a current circulating. That means if there's a curve of your E, then the current is circulating. So curl E cannot be zero. If it's zero, then there will be no voltage. Okay, so this set of slides is important for you to know how to calculate that Faraday's law. Okay, so just now I said generator is this principle. The second one is induction. The induction method is like a transformer. So you have a primary coil. The primary coil, you actually pump charges. You move charges by your source, electric source. But you must move the charges such that it's not constant velocity. Its velocity has changed with time. So once you have a time varying magnetic field, then you can generate time varying flux that couple across to this secondary coil. And that creates this EMF. This creates this curl E. Okay, how exactly is it done in the quantification part is Faraday's law. This is Faraday's law. The EMF generated, first you have to take the magnetic flux density, multiply by the area to get the total flux. Get the total flux. Why is it double integral? It's just to ensure that the area is small enough over the B is constant then, right? If of course if your B is uniform, then the whole thing here is just times your area, B times the area. Next, you have to find out how it changes with time. That's why we say you can only generate EMF if it's time varying. If the velocity of that, the velocity is, if it's constant, you cannot. It will be zero. Yeah, it goes to be time varying. So that's this ddt part. This minus is actually Lenz's law. Yeah. Yes. Okay, so that's the equation you're going to use to solve your question one. This is the equation you're going to use to solve question one. Okay, I think the rest is you will see very many cases of solving different examples. So 11-2 onwards will be all on application of Faraday's law. So make sure you go through it. But as you go through, always try to understand back to that formulation, like what we did for electric field, like what we did for magnetic field. So in this case, the formulation always start from that flux, small flux by a small area. Yeah. Yeah, so I don't think I want to open up all of them. In fact, all of them are on that. Okay, some are on the generation. That means you have movement in a static magnetic field. Some are induction, meaning you have a time varying magnetic field. Okay, so you have to go through all this to solve next week tutorial. So then you may ask, does that mean I don't need to go through any of the lecture slides for this week? Okay, what is this week lecture slides? Very first one. Displacement current. Okay, if you just target at solving next week tutorial question, no, you don't need any of this. But don't fall behind because you have to complete this week's lecture plus next week's lecture to solve next tutorial, the tutorial 6. So I will advise you try to at least go through the first two. Yeah, otherwise too much for you to go through later on. Yeah. So the tutorial 6 is on waves already. Yeah. You see it's on waves. More exciting really. Yeah. And how many of you already done the experiment on waves? Not yet, huh? When are you doing your experiment on waves? Next week. The whole class next week. Are you you're already done? Are you very confused by it? Yeah. Polarization is confusing to you. Okay. What is the electromagnetic wave? What's the electromagnetic wave? Yes, 3 vectors, okay? 3 vectors. What is this vector? What is this vector? What is this vector? EH, direction of propagation. Propagation. Yeah. So the wave can be traveling like that from the transmitter to the receiver. You notice the E field remain constant as they travel. This is what we call linear polarization. If the wave as it travel, it twists, keeps twisting, then you end up circular polarization. Okay. Linear polarization, the E field, if it's in this direction, always is called horizontal. It can be like that. This is called vertical. So those of you who did an experiment, you use a wire mesh, right? Put in between. You see, wire mesh means there are vertical conducting wire. I mean, there's vertical conducting wire, depending on which angle you put it. You put it like that, you'll be conducting like that, right? You put it like that, you'll be conducting like that, right? Now you tell me, if I have an E field like that, linear horizontal, when you come to this wire that is horizontal, what happens? What happens? I conducting wire this way. Can I have voltage difference left and right? No, right? Because the 0 ohm, it force the potential to be the same. This electric field, if it's in this direction, needs a potential difference, right? So what happens? It cannot go through this. If you have a conducting wire, it cannot go through. What happens to it? What happens to the wave if it cannot go through? What do you think will happen to the wave? Yes, exactly. It will reflect back. It will reflect back. Okay, that's what happens. It will reflect back. Cannot go through. Okay, then you rotate the thing until it's like that. The wire is like that. Can you pass through? Yes, can pass through. Many of you give the answer, hey, I see the wire like that. You pass through the gap of the wire. No, that's wrong reasoning. Okay, so always think of the voltage because E field require a voltage difference. Polarization of a wave is the direction of the E field. Okay, I think the other aspect of that is really talked about phase because this is AC signal. So if my signal travel from transmitter to my receiving point, as it travels, the phase changes. So if I have a second path that hits, say, ground and go up, there's a path length difference, which result in 2 vector. These 2 vector, they can be in phase if the path length is exactly 1 wavelength. They can be out of phase if it's half wavelength. So therefore, depending on this path length difference, the signal can go up and down. Yeah. So what creates this extra path? Yeah, it can be like you put a plate, right? Metallic plate. When the ray hit the metallic plate, that sharp edge creates what we call diffraction. It's a secondary source. You have rays going in all directions. So the one that goes there to your receiver is what you're interested in. Yeah. Okay, anyway, all those concepts are more actually, you see tutorial 6, tutorial 7, many more actually. Most of the experiments there are all the way until I think easily up to tutorial 10. Up to tutorial 10, I think only the last 2 tutorial is out of this wave propagation side, which is more in the conducted case. Yeah. Conductor case, like for example, you build high frequency circuits. So now your circuit actually conduct a wave. Yeah, at high frequency. Yeah. Okay, I stop here. Any questions from those in the internet? Okay, thank you. Just one moment. I want to make sure that I got all your attendance. So those of you who have not signed the attendance, please sign it. Those on the physically online, let me read out the name that I already have. Guo Weiwen, Ding Wei, Guo Weizhang, Lai Ziqing, Kanaka, Sun Yiquan. I'm not sure if I've got all your name. I'm trying to scan and see. Wendy's name is not there. What's your full name, Wendy? Han Wendy. Okay. Who else? Mohammed Maru. Amiru. Okay. Yeah, I got you, Amiru. Anyone else? Wei Wen, Wei Zhang, Sun Yiquan. Ziqing, yes. Xia Song Cheng, okay. Just a moment, let me just complete this. Ding Wei, okay, good. Tanaka. Huan Sun Yi. Oh, okay, Sun Yi Quan, okay. Okay, I think I got everyone now. Okay, thank you guys. See you next week.